when I guess DeepSeek was already big, but it wasn't that big at an absolute apex of hype. Okay, so the paper for V3 is pretty big, and it goes all over the place. I will not cover everything from there. I will skip some of the data preparation parts and whatnot, but we're going to dig very deep into the things I understand well, and we will not dig very deeply into the things I don't understand well. So architecture-wise, so generally, what's cool about DeepSeek? It's a state-of-the-art model, which outperforms many other open source models and closed source models. And allegedly, it's extremely cheap to train, right? And so there are multiple reasons for both of those achievements, right? So presumably, the performance has a lot to do with data preparation, which paper doesn't go very deep into. But the speed of training and the cost of training, especially given that they have hardware which is inferior to the hardware we use here, right? They use H800s, which is the same as H100, but the speed of communication is twice as slow. It's an intentionally, intentionally crippled GPU for like whatever regulations and whatnot. Okay, so because they had worse hardware, I think that's the irony is that because they had worse hardware and the worse networking, they had to figure out how to make it work, and so they made a lot of advancements that wouldn't happen otherwise, right? Okay, let's begin with the first one in the paper, multi-head latent attention. So on the left here, I have the basic attention, right? Yeah, you have the input vector. In this case, it's called HT. So HT is whatever coming from the previous layer or from the embedding, and then you compute. You have three matrices: W, K, W, V, W, Q. Oftentimes, it would be a single matrix that you will later splice into three. And you multiply So here I use the same notation that they use, where you multiply matrix by vector. But in reality, what happens is that you're not using a single vector. You have a whole batch of inputs. And so what you actually do is you multiply the batch of inputs by the matrix, right? So it's going to be the other way around. But right, so you multiply input by those three matrices, you get keys, values, and queries, and then you compute inner product of keys and queries and keys, and that for every token, like for a particular token for which you're computing the attention, it will give you the similarity of the query to each of the keys preceding it, and then you multiply that similarity by the values, right? So here, a couple other details is that for keys and queries, you also compute positional embeddings, which today almost exclusively are ROPE, which stands for rotational positional embedding. Okay, so let's look at what they do differently. So the problem they're trying to solve is that after you computed those keys, values, and queries, you need to keep the keys and values in memory for the future tokens, and memory is at the premium. So ideally, you want to reduce the amount of memory you consume. So what they do is they, instead of computing keys and values directly, they do something very similar to what LoRa does. Namely, they multiply the input vector, which is wide, by a matrix which projects it into a smaller dimension, much smaller dimension, right? And then they multiply by another matrix which up projects it back to the original dimension. And the key here is that the keys and values that they store in memory are the small down projected, right? And so they occupy much less memory. But also, as a side effect, multiplying by down projection matrix and up projection matrix is cheaper than multiplying by single square matrix, right? So they both save time and memory, with the caveat that because they only store down projected version of keys and values, they have to recompute, like they have to up project, right? So like when you use multi-head attention, for each consecutive token, keys and values already stored. You only do inner product and softmax multiplied by values. But in their case, they only store the blue ones in memory, right? So this, like here, they have to recompute keys back, right? So they have to multiply by up projection matrix again. They have to recompute values multiplied by up projection matrix again. But presumably that is still cheaper than full multi-head attention. Another interesting thing, maybe that's how everybody does it, but that's not how I saw it being done, is that generally, so the way rope works is that it takes every pair of, so like you have a vector of size 2048, for example, it takes every pair of consecutive elements and rotates them by different angle based on a particular rule, right? And so usually people just apply rope to the actual vector that you get as a result of, for key or for query. They don't do it this way. They compute two different keys, and to one of them they do apply rope, but to another one they don't, right? So part of the key, right? Yeah, the question is why is there no information loss when you go to the like the beauty of the transformer, right? That initially transformer is completely random, right? So whatever constraints you put on it, it will train under those constraints, right? And like people have been studying it for a while, but there is still a lot of places where you can, like where it doesn't need all the resources given to it. So presumably for keys and for like a very good example is group query attention, right? So group query attention. Like back in the day, you would compute as many keys, queries, and as you have values, but eventually people figured out that you can. Yeah, and there was some other reason why they apply rope, not on the whole vector, but only on part of it. I don't remember it now. Maybe as we go, I will remember. Okay, now the next thing is that the actual model is the mixture of experts. We've seen mixture of experts before. I think it's pretty well known that all the GPT is a mixture of experts. Mixtral is a mixture of experts. Okay, so very quickly, what is mixture of experts? Here I have an example where you feed a token corgis, and it goes through the whole transformer. Right? So the transformer consists of embedding, which embeds the token into the space in which the model can reason. Then it goes through multiple layers, and it does unembedding, which gives you potential tokens, right? And every layer does two things. It does attention, which we just discussed, and after the attention, it does what is called MLP, where without mixture of experts, it just multiplies it by a matrix, which is learned, applies nonlinearity, Swiglu in case of Llama, and in case of DeepSeek, then multiplies by another matrix, right? So here, the thinking is that instead of always multiplying by the same matrix, which is like one size fits all, what you can do is you can have multiple matrices called experts, and then for each row, for each token, you first run, like let's say you have 16 matrices, 16 experts, you first run it through a matrix of the size, dimension of the model time by 16, and it gives you the confidence of the model in terms of which of the experts is the best for the token, right? Then you sample some number of them, like let's say 2, and then you use those two matrices to compute the MLP instead of using the same matrix, right? And the original idea behind mixture of experts is that the total number of parameters now is much bigger than the number of parameters you actually activate on the forward pass, right? And so if the model learns to use those parameters efficiently, you get a more capable model cheaper. The second advantage is that you can have those experts to be on different GPUs. Well, I guess it's not. Yeah, you can have those experts on different GPUs, effectively spreading parameters into different GPUs, and then you can apply MLP efficiently, taking advantage of all the parameters, right? So in this case, I have on top a simplified version of a mixture of experts here, right? You compute, so X is the input, and at is the PyTorch way of saying matmul. You multiply it by G. So G would be dimension of the model times 16, or like times number of experts. It gives you the probabilities of each expert, you softmax, and then you sample one expert or several, and then you compute input times the expert nonlinearity times the second expert. Okay, so a couple things here. A is, so here's a sample. In reality, in DeepSeek, they don't sample, they take top one, or like top K, right? So if they want K experts, they will not sample K of them, they will just take the top ones. And they, so let's look. On the bottom, it's the same. Let me see. Okay, right. So G would be, so capital G is the probabilities of the experts, right? Then you sample multiple experts, K of them, not one. And then the output vector would be the sum of, okay, yeah, now I see the key here. So the interesting question is, how do you train the matrix that will be predicting probabilities of experts? It needs to be learnable, right? Because if you only use it here to sample or like to choose top K, that's a non-differentiable action, right? So the gradient cannot flow. So what they do is when they choose several experts, like K experts, right? So K has to be more than one. When they choose K experts, they multiply the output of every expert by the weight that was assigned to the expert, right? And then they divide by the sum of the weights. So the expected the expected magnitude of the output is the same as the expected magnitude of each expert, right? But this multiplication is differentiable now, right? So on the backward pass, if one of the experts was giving a better, more useful output than another, then the gradient will flow and say, hey, it would have been great if that expert output was multiplied by a bigger number, right? And so the expert matrix now can learn. The problem is that initially the model is completely random, and one expert will start learning a little faster than the others naturally, right? And so the model will say, oh, that expert is better, right? Let's give him higher weight, right? And so some experts will be getting higher weight. Now, you will notice here that on the backward pass, if you think what is the derivative of product, right? The derivative of product is like derivative of kx is k, meaning that the gradient which flows into the expert is scaled by the probability, right? So if an expert is chosen with a smaller probability, it also gets less gradient, right? So now the expert which is already smarter and gets chosen on itself is also learning faster, right? And so what happens eventually is that there's a complete collapse where one expert is always chosen and is being trained, and all other experts have zero weight, no gradient is flowing, they do not get better. And so the way people deal with that is they introduce a separate loss, auxiliary loss, which penalizes if the experts are not chosen uniformly. And the problem with it is that if you add this auxiliary loss, now you have two losses. One loss says, hey, predict the best token possible, and another loss has nothing to do with the quality of the token, right? So that loss is tampering with the learning. And so that is something, yeah, so this is a paper, a very old paper from Google that introduces auxiliary losses called outrageously large neural networks. And this is like at the bottom, you see the loss they propose to use as an auxiliary loss. Anyway, in the DeepSeek V3, they completely remove the auxiliary loss. And the way they do load balancing is they introduce a bias, right? So there's another learned vector called B, though B is not learned through gradient descent. Instead, so G, you will notice here that G is used for two things. You use G to sample experts, and then you use G to multiply the output by the probabilities, right? So they compute now two G's, G and G prime, where G is what you will multiply the output by, and G prime is the probability, right? So they decouple them. And for the probability, they add the bias. And the way the bias works is that they run a whole batch, then they look which experts were chosen how many times, and if a particular expert was not chosen sufficiently frequently, they bump the bias. But because it only affects sampling, so it's not sampling again, so it's top K in their particular case. But because it only affects choosing the experts, but not the actual computation, that bias does not influence the output in the like it doesn't tamper with the output in any way besides the expert choice. And I don't remember in the paper whether they use this bias at the end when the model is fully trained, like during inference time, but presumably no. Like during inference time, you can probably just drop it. And so this way, you have pretty high certainty that the experts will be balanced because the bias is consistently balancing them without having any auxiliary loss, without tampering with the quality of training. That also, so the thing about mixture of experts also is that you want, not only you want experts to be balanced for the sake of them all learning, you also want them to be balanced for the sake of computation, because if one expert has way more tokens than another, then assuming they're on different machines, which is the case in their case, right, that computation will be longer than, like the computation is now not balanced, right? One machine will be computing longer, another one will be idle. And in their case, because they're pretty balanced, they don't, like if you read Google papers, you will find in many of them that they drop tokens, right? They will assign tokens to experts, and if some expert has more than some threshold of tokens, they will just drop some tokens. Like some tokens will have no computation made for them. And in DeepSeek, they say, hey, we don't have to drop anything because the balance is pretty big. And the only thing, I don't have it here on my slides, but they do add a little bit of auxiliary loss to make sure that within a particular sequence, the experts are somewhat chosen uniformly. Cool. And another thing, I think that's the last one in the architecture, is multi-token prediction. So effectively they say, well, we have the input token, we did all the expensive computation of the transformer, and at the end we only predict one token. But in many cases, presumably you have enough information to predict a couple. Like if you think how we think, we usually have, like we don't need to know the next word we're about to say to know our thought, right? So it makes sense to reuse this expensive computation with a lot, like on this picture, something to pay attention to is that in the leftmost block, there's L transformer blocks, there's L layers, and L is a pretty high number. It's like between 60 and 90, right? But in the second and the third block here, there's only one transformer block, right? So what happens is that you feed the sequence of tokens, like the first 4 tokens, into the transformer. It goes through all the layers, goes to the output layer, predicts one token, and then this final vector that goes into the output layer, it goes into one more transformer block, does that transformer blocks, goes into the output layer, predicts the token after next, right? And so that gives you more signal that allows you to train this, it's more loss, more signal with a very low cost. And on this picture, they show multiple tokens ahead of time. In reality, in practice, they predict one more, right? So in practice, they predict the very next token and the token after next. Cool. That is also presumably could be helpful during inference. I don't know if this is used anywhere, but because you can sort of pre-predict next token, I don't know if this is used in any way. Okay. Now, this is the next section, which is the engineering behind DeepSeek. So training generally, distributed training is relatively complex because you're doing a lot of computation and you're doing a lot of communication. And ideally, and communication is expensive. And in their case, communication is twice as expensive because they have crippled hardware, right? So you want, ideally what you want to happen is you want, whenever you do communication, to do some computation at the same time, right? So if you're doing some computation when communication happens, that's like effectively your communication is free, right? And when you do model scaling, there are multiple approaches to it, right? One is called model parallel, where when you multiply one matrix by another, you can slice one of the matrices, move them to 8 different GPUs, right? And then you compute 1/8 of the math mole on each of them and do all reduce. This is something that DeepSeek doesn't do at all, because I guess with their overhead of networking, it's too expensive. Then the other one is expert parallel, where every GPU is running a different expert, right? And so after you compute the expert assignment, you dispatch the rows to the corresponding experts, compute the experts, and then you combine back the data, the outputs. And then there's obviously data parallel, which is effectively saying, hey, we're going to have the copy of the model many, many times, and we're going to be computing on different batches at the same time, different mini batches. And then there's pipelining. So the idea of the pipelining is you slice the model vertically, meaning that the first, like one GPU will have the first several layers, the next GPU will have the next several layers, next GPU will have the next several layers, and then the input comes into the first GPU, it computes its share, sends data to the next, and as the next GPU starts computing the second set of layers, the first one is ready to compute the second batch of inputs, right? And so here on the picture, you will notice, like naturally, when you just begin the batch, right, only the first GPU is active. All other GPUs are blocked, right? So here on the picture, you will see the green is the first batch of data, right? And you feed it to the first GPU, the second one is idle, right? And so in the middle, you will notice it's very busy, right? So once the pipeline is busy doing stuff, it works great. But at the beginning, at the end, you will have those holes. And because generally you want to keep your batch relatively small, the reality doesn't look like this picture. The reality looks like this picture condensed horizontally, meaning that the percentage of the wasted time is actually much higher than on this picture. But also another problem is, so here on this picture, the squares are forward pass, and the wide rectangles is a backward pass, because backward pass is generally slower, right? And so here you will notice that, like if you look at the yellow batch, right, it does 4 forward passes on different GPUs. Then after the last one, it computes the backward pass, and then it goes backwards, right? And so here, everything here is condensed. However, look at this. You can see my pointer, right? So here, the blue one has finished the forward pass. It sends data to the next layer. And the next layer just finished the yellow backward pass, sends data back. And here, if you draw it on the paper, you will notice that there is no way to overlay communication and computation. You have, like at some point, they all have to stop and do communication. There's no way like to move them in a way that there's no deadlocks, which is highly undesirable. Ideally, you want to do pipelining in such a way that whenever there's any communication, someone is doing computation. And so they do it differently. To understand what they do, let's quickly revisit all the steps with expert parallel, right? So the first thing you do, so you have the input vector, input batch from the previous layer or from the embedding. It's on every machine, right? All of them can do attention, that's compute. Then after attention, they assign experts, that's compute. Once experts are assigned, they dispatch. Dispatching is networking. Now every machine has their share of every expert has the share of inputs. They compute the expert, the MLP. Now they have to combine their outputs, that's networking, send to the next pipe depth, also networking. If that's the last layer. If it's not the last layer, it goes back to attention, right? And on the backward, you do all of those in reverse, right? So combine prime is dispatch. So now you have the output gradient coming from there, and you need to send it back to the experts, right? So it's the derivative of combine is dispatch, right? So combine prime is dispatch, FFN dispatch prime, which is combine, expert assignment, backward attention. Okay. Okay. So the key to their optimization is to remember what is the backward pass for the MLP layer. For the MLP layer, for the matmul, on the backward pass, so on the forward pass, you have X, which is the input to the layer, and W, which is the weights. And you compute the output as a matmul. On the backward pass, you compute the derivative of the input for the chain rule. For that, you get the derivative of the output that came to you from the chain rule and multiply by the weight matrix transposed. And then you compute the derivative of the weights. That's the actual gradient that you want from the backward pass. And that you do by multiplying the transpose of the input with the output gradient. Now, the key here is that the X prime you need to send back, right? So before you can send to the previous pipe depth, you have to compute it, right? There is they have to be serialized. But W prime is not blocking anything. This is your final computation. It's a leaf of your graph of computation. So you can compute W prime whenever. Whenever you have free cycles, when you're doing some communication, you can compute W prime. And so they have this picture, there's a couple of things to pay attention here. The thing to pay attention, number one, is first of all, let's see what's depicted here, right? So the green one is a forward pass. Sorry, the yellow one is a forward pass of one batch. The green one is the backward pass of another batch, and the blue one is the backward pass for the same batch that computes the weight gradient, right? So this is yeah. So this is yellow for one batch, this is green for another, and this is blue for another, right? So a couple of things to notice here. One is that they're not aligned in the sense that you will notice that for the yellow one, sorry, for the green one, it begins here, right? So it begins with MLP. Okay, I should have, so FFN is MLP, right? So it begins with the FFN, with MLP, then dispatch, then it doesn't show expert assignment here, but then attention, this is attention, right? And sending back to the previous pipe depth, this is PP. So PP is sending, is the pipelining, the communication. But for the forward pass, it begins in the middle, right? It begins with dispatch, which is right here, right? So they're not aligned. The backward pass and the forward pass are not aligned. They like slightly shifted relative to each other. The second thing to pay attention here is that if you remove the blue block, you would still entirely or almost entirely overlay communication and computation, because presumably computation is slower than communication, right? So here, if you imagine removing completely MLPW, on top you would still MLPB, like dispatch F will just get smaller and dispatch B will get smaller, because here you don't use, like you don't need, oh, sorry. Like if you look at this graph, the green MLPB is a math mole. Dispatch F is sending the experts. Presumably dispatch F takes less time than MLP, right? So part of this time is not actually spent on networking. So if you remove MLPW here, you would still have computation here and communication fully overlapped. And right, so dispatch F will finish while MLPB is being computed, right? So by the time you're ready to start MLPF, you have the data and you're ready to dispatch B. On the right side, I believe it is also the case, right? So if you remove attention W here, attention B, so after we're doing attention B, we need to send to the next pipe depth. This is blocking before we can do combine, right? So attention B, some pipelining will have to happen here before we combine. And to combine, some pipelining before attention F. But presumably, you can fully overlay it in a way that you do combine F, this is this one, right? Then while you're sending to the next pipe depth, attention B is still being computed, right? And so by the time you send the combined data to the next layer on the forward pass, right? So attention F is ready to be computed, attention B just finished, so it's ready to do its pipelining, sending to the previous pipe depth, and then you're ready to combine, right? So the key here is that you can remove the blue ones and still have computation and communication fully overlaid, right? This is not emphasized in the paper, but it is clear from this following picture that they show, where they show an example of pipelining, like it's a whole example of multiple, like descent. So there's one other thing here, which is they don't have a single, every device has not one, but two different pipe depths. So it's like, for example, here, the device 0 has the first pipe depth and the last pipe depth. And the second one has the second and the penultimate. The next one has the third and the third from the end, right? And so this way you can start sending data from two ends, which further reduces the bubble, right? And so here, and they only annotated the top one. I annotated a couple of bottom ones here, right? So A, B are also two batches, right? So that you can see where they're going, right? And you will notice, right? So at the beginning, they start multiple forward passes. So at this point, no backward can be computed because, still no forward pass has been fully completed, right? And then at some point, the forward passes have completed, right? And you see A here, or rather, let's look at the one they annotated, right? 0 here, it has completed the forward pass. It completed the backward pass, and now it's it could have already computed one. Like I guess 1 and 0 here can be swapped, the blue one and the yellow. But the key here is that no matter how you arrange them, if you remove the blue ones, there would be some bubble, right? So they have some available computation, and they fill it in with blue. They fill it in with computing the weight gradients, right? But here in the middle, where the pipeline is fully busy, you will notice there is no blue, right? Go ahead.
What exactly is the blue one? Green, I get is the backward.
Yeah. So the backward pass consists of two things: computing the input gradient, computing the weight gradient. Computing the input gradient is green, computing the weight gradient is blue, and the weight gradient is not sent anywhere over the network, so you can compute it at any point.
Wait, why is the separating the gradients are always computed? Yeah, you can do both the gradients together, right? Why is there a distinction?
You can. The point is that you don't have to, right? Like the point is that in order for the chain rule, you have to compute the input gradient before you send it, but you have an option to compute the weight gradient later. You don't need to compute the weight gradient to send the input gradient backward, right? So part of the computation you can delay until later. It's not blocking you, right? And so that gives you flexibility in arranging your pipeline. And here you will notice that, but importantly, you will notice that in the middle, when the forward and backward passes are fully overlapping from multiple mini batches, they do not compute at all the weight gradients, right? Because they can fully utilize the computation, and at the end, where you would have a bubble otherwise, they compute the tail of the blue ones. Actually, in retrospect, I might be wrong here. It could, oh yeah, sorry. I think the wide green means green plus blue. Yeah, but potentially take back everything I just said. Yeah. The white green is green plus blue. It's both. It's both backward for input and backward for weights. Okay, so that also means that potentially my statement before that you can remove the blue here and still fully overlay communication computation might be incorrect, right? There's a good chance then that dispatch F is actually taking longer than MLPB, right? And then this blue in the middle is what enables. Okay, so that's pipelining. So in general, I think, again, like the irony of the fact that because they had slower network, they had to be creative here and come up with all those cool optimizations is pretty interesting. Okay, quantization. Initially, I didn't plan to talk about quantization today, so I don't have all the slides, but I think quantization is very interesting. So quantization during inference, I guess everybody's using quantization, right? You get the model, which is trained in FP16 or BF16, and then you quantize it to like 8 bits or 4 bits or even smaller, right? So that you can run it locally on your machine. But training with smaller precision has been challenging historically, right? Because you do need, for certain operation, you do need the precision, right? And so here they go into quite a bit of detail how they manage to train in 8 bits. And so the key interesting ideas here, one is that when you do 16-bit training, you usually just use BF16, right? BF16 is a floating point format where, I guess, exponent is wider and mantissa is narrower, and then FP16 is the other way around, right? So, but with BF16, you just use you just use whatever the actual range of the format and don't do any rescaling. But when you use FP8, you cannot. You only can represent 256 different values, right? So the actual range of the type is not adequate. So they do rescaling, and there are two things here which are interesting. One is that how many bits they allocate for mantissa and for exponent, right? And the other one is what is the range, sort of the range of the FP8. What does it map into? And usually what people do is that they get a tensor, they compute the minimum and the maximum value and say, hey, FP8 will just map to the range from the minimum to the maximum value, right? But that obviously degrades the bigger your tensor gets, right? So it's one thing if your tensor is 256 by 256, right? Then you only have 65,000 values, right? But if your tensor is 4K by 4K, suddenly like the outliers, the min and max value can significantly reduce the precision of FP8. So what they do instead is that they quantize per some number, like they don't quantize per tensor, they quantize per like slice of a tensor, right? So for input, for example, they take a single token, they take 128 consecutive values in the tensor, and they only use those 128 to find the minimum, the maximum, and scale those 128 to that range. And they get the next 128, compute the minimum, the maximum, and scale there, right? So they quantize per slice, and because of that, no matter how big the tensor is, the quantization quality remains the same. And then because of that, I guess there was some previous state of the art in terms of training FP8, and in that approach, they used 3 bits of mantissa, 4 bits of exponent for forward pass, but for the backward they would use only 2 bits of mantissa, 5 bits of exponent, because for backward they needed more range. But they say, hey, with our quantization strategy, you don't need that. You can use 3 bits of mantissa, 4 bits of exponent, both forward and backward, which increases the precision. Okay, cool. Then certain things need to stay in high precision. I guess one thing is the actual weights are always in FP32, right? And the gradients are always in FP32, right? I think those are the only 2 things. Maybe there's a couple more. And I think here one arrow is missing, or maybe I'm misreading the picture, right? But in Adam, so the biggest memory waste besides the activation during training is Adam, right? Because you need to, like naturally you have to store the weights, and then you need to store 2 tensors per. So for each tensor, for each weight tensor, for each parameter of the model, you have to store. You need to have 1 more tensor for the gradients, and then you need 2 more tensors for Adam, 1 with momentum, 1 with a second order momentum, right? And so they say, well, those 2 can be BF16. That's chill. The gradient has to be FP32, and the weight has to be stored twice in memory. 1 is in FP32, 1 is in FP8 for the actual matmul, right? So this is a little bit of overhead, but despite this little overhead for the weight, then you can have significantly smaller, like the input activations can be FP8. They also ship them over the network in FP8, reducing the network overhead. Right, all the matmuls, except for attention. Attention they don't do in FP8, but all the matmuls for experts are FP8, and then they aggregate in FP32. And then there's a part of the paper which I did not. I think my knowledge of CUDA is not sufficient to understand it, but evidently for some reason aggregating in FP8 is not trivial and required some engineering. Cool. Yeah, but anyway, training in FP8 is possible, and that's pretty cool. Okay, pre-training. They talk about a couple of things. One is, so there is this concept called fill in the middle. The idea is that it would be great if we could not only predict the next tokens knowing the prefix, but if we were also able to see the prefix and a suffix and predict what is in between. Like if you think of Copilot, right? The Copilot doesn't just see the prefix of the code; it sees everything before the cursor and everything after, and it needs to fill in what happens in between. So the way people do that is they convert a subset of the training set, right? So you have a training set like 15 trillion tokens or whatnot. You get a subset of it, some percentage, and for that percentage, you rearrange the tokens, right? So you say you insert a special token called FIM begin, then you put the prefix, then you say FIM whole, put a suffix, another special token, middle, and the final token, right? And then just part of your data set is in this format. And what the model learns to do is it says, hey, if I see this special token, and this special token, oops, then what I'm starting to predict here has to be consistent with this beginning and this ending, right? So the model is just naturally learning to predict the middle. And the only concern that you might have is that if you can, like, let's say you're converting 10%, this is what they do. They convert 10% of the input data set to this format. That means that for the 10% of the data set, you don't see it in the proper order, right? And so the question is, does it affect the performance? And the answer is no, right? So 10%, if you convert 10% to FIM, the performance of the model on the regular non-FIM inference is not affected at all, right? So converting 10% is acceptable, and then you get the FIM model, right? One interesting thing that is not mentioned in the paper that quite a few people, when they train FIM, they swap the suffix and the prefix, right? And the beauty of that is that if you swap the suffix and the prefix here, then you don't need a separate token between prefix and the middle, because prefix and the middle, like the middle is a natural continuation of the suffix, of the prefix, sorry, right? So you would have a suffix, special token, and then you would have just everything before the suffix, right? You don't like here, you have to choose 2 places where you split the sequence. But if you do suffix, prefix, middle, you only choose 1 place to split, right? And then you like effectively have infinite number of middles for free. They don't talk in the paper why they chose this approach. Yeah, and another beauty of a suffix prefix middle is that presumably the prefix is more important for the middle than the suffix. So it's great if it's close, right? Because obviously transformer learns to utilize the recent data better than the old one, right? So if you do prefix suffix middle, by the time you do middle, your prefix is very far behind. But if you do suffix prefix middle, then by the time you do middle, the prefix is right here available to you. Cool. Yeah, so they do fill in the middle. Then they have a very large context window, and naturally nobody trains with a large context window from the beginning. People train with a smaller context window and then they upscale it. And here I have the formula. So this is like if you were reading Hacker News, like, I don't know, a year ago, Georgy Griganov was showing that, hey guys, I managed to increase the context window of Llama, right? And the way he did it was using this formula where, like on the left, you see, so the only thing you need to change is rope, right? And everything else is unaffected, but the positional embedding has to be changed. And here on the left, before the left side, before the equal sign, is how rope is usually computed, right? You have the input token, you have the position in the sequence and the frequency, and they say, well, if our old maximum was L prime, sorry, our old maximum was L prime, our new maximum is L, then instead of feeding the current position, we will feed the position times old times new divided by old, right? So effectively you stretch the positions in a way that the range of inputs to this parameter remains the same, right? And if you just do that, the model will break. So anyway, this approach works, right? So like, we know that if you get Llama, for example, with a short context, apply this to rope and just keep on training it for, I don't remember the number, like 100,000 examples, million examples. It learns to use the longer context and gets pretty good at it. But there's this paper called Yarn, which digs deeper into it, and they analyze. So the way, again, rope, we didn't get very deep into how it works, but the way it works is that every 2 consecutive tokens, the vector by which they rotated, the frequency at which rotation happens is different for every position, right? So for the first position, the frequency is very quick, right? So every couple tokens, it will do the full circle. For the next one, it's slower. For the very last 2 tokens, it goes very slowly, like maybe not even doing the full revolution throughout the sequence, right? And so the people in the paper, in the Yarn, it's generally a very good paper to read. It's very insightful. But a couple of simple insights is that for the small frequencies, the actual values, like you don't want to stretch it because the actual relative value between 2 consecutive tokens is very important, right? Because for recent memory, you would be looking, like, if you need to look 5 tokens back, the model sort of learned the exact rotation it needs to apply to get there. If we stretched it, it will now overshoot and look in the wrong place, right? So in Yarn, they say, hey, for the small frequencies, let's not stretch them. Let's keep them like as is. For higher frequencies, it makes sense to stretch them because, it's like for looking for older stuff. And there's more insights there, right? They have 3 different approaches to look at it, and every approach gives them different insights for different frequencies, and then they have like a final modification which works better than this simple formula. And DeepSeek is using Yarn. Okay. Now, V3 and R1 are heavily interdependent. So if you download the V3 paper, the one they published originally before R1 became a big thing, you will notice that the tail end of the V3 paper actually has most of the R1 information already there, because R1 was used in the post-training step of V3. So let's talk a little bit about R1 and then how they are used to train each other. Okay, so first of all, a very quick insight into PPO. So they use their own reinforcement learning approach called gRPO, Group Relative Policy Optimization, which is a flavor of PPO. PPO is a paper by John Schulman from very long ago. I think it's 2016. What the basic idea is here. I don't know if you can highlight it in a way, but the core idea is that you have a policy, a policy is your generative model that produces your outputs, right? And then you want your model to get better at a particular task for which you have a way to estimate the quality, right? And so you have so here you will see bias policy, right? So policy old is the policy that you have right now on the previous step, and the policy without all the policy. My Greek is not up to date. I don't know how you say this letter, but the new policy is the policy you're choosing, to replace the old policy with. And so there's a very old algorithm called policy gradient, which effectively says, hey, let's optimize this, right? This part, like effectively the behavior of the, so you have some set of queries. So queries is something you sample from a set of queries you can use. Then output is some output from the policy, right? And then you say, hey, I have some number of those queries. I will sample old policy and the new policy. And then I will compute what is called advantage. Advantage says how much better the new policy is better than the old one. And then I will optimize. This function, the expected value of the advantage multiplied by how confident the new policy in a particular trajectory divided by how confident the old policy is, right? So if there is some trajectory for which advantage is high and the new policy is much more confident, you want, to give her a reward. If the new policy, there's a lot of advantage, but the new policy is just, slightly more confident than the old one, then, you give it a little bit of reward. Anyway, so this is very unstable. And the way PPO is fighting it is by doing two things. One is they clipping this value, right? So this ratio is clipped between 1 minus epsilon and 1 plus epsilon, right? So you cannot, like if your policy is 5 times more certain than the old one, you're only getting reward for 1 plus epsilon. And the second one, so here I use the formula from the paper, from the DeepSeek paper, but if you go to the old PPO papers, you will see that there were many other ways to do that. But the idea is that there's also another policy called reference policy. Reference policy is your model before you even started reinforcement learning, right? So you have 3 models. One is your original model before reinforcement learning, and then at every step you have old and new. Then you go to the next step where the new becomes old, you have old and new. And you're effectively saying that the KL divergence of the final model from the reference model has to be as small as possible. Effectively, the reinforcement learning says, get as good as possible in this skill, but not deviate too much from what you already know, right? So this is, okay, so there are 2 problems here. One is that advantage is generally computed using yet another model called value function, right? So effectively we say, hey, this is the reward we computed, and this is what we expected it to be, right? And the value function is hard to train, and that's another model to maintain in memory, right? So it's an unfortunate thing to have here, and I guess the second problem they mention is the way the KL divergence is applied. They move it. So they move it here, right? So they make 2 changes, right? Like if you look at this formula, it is exactly the same as PPO, with the difference that they subtract the KL divergence in the actual expected value, not per. So here it's per sequence. Here it's computed once, and that is something like if you open the original PPO paper, I think it also does it this way, right? So I guess there are many ways to apply KL divergence, but the actual key here is that they don't have a value network. Instead, what they do is that they sample, they create multiple, give me 1 second. Yeah, they compute multiple, they enroll policy multiple times. They enroll it, let's say, I don't know, 100 times, right? So they have 100 different sequences, and they compute the reward as a reward minus, like effectively, the advantage is how much better the reward of this output relative to all the rewards we collected across all 100, right? So instead of having a value network, they estimate the value function by averaging a lot of outputs together, right? So that gives you that allows you not to have a value network. And we, like by now we know that this works very well, right? Because if you go to Twitter, a lot of people tried this exact approach on smaller networks on a lot of, every several hours someone is publishing new results, and gRPO works. So this is a pretty cool reinforcement learning algorithm. Go ahead.
So the RI is the ratio, right, between the byte data and byte data on. The RI there.
No, RI is the reward.
Okay, and so you're not. It's not linked to that ratio.
Yeah. Okay. Let's quickly, I guess, go deeper. Right. So what happens, right? So we begin. So we have, again, let's say we already did multiple iterations of reinforcement learning, right? So we have the current. So policy is the fancy name for the neural network we have for the transformer. So we have a reference policy. That's the one we started with. We have the old one. That's the one we just computed, and then we're about to have a new one. Right. So we sample multiple queries. So queries will be the tasks on which we evaluated. Right. So we have multiple queues. Then for every queue, we use the old policy, the current state of the model, to sample G outputs. Right. So you have multiple trajectories. So you have some math problem, and you sample from the current policy like 100 different thinking trajectories, and each of them results in a particular output. And then you compute reward for each of them. So RI, so here I is from 1 to G, and RI is the reward, right? Which in case of a math problem would be 0 or 1. It's either correct or not. But in case of some other applications, it would be, potentially more insightful, more granular. And then you compute the value function, the loss function as you take each of those outputs, you compute the probability of this output under the new policy and under the old policy, and then it's clipped, right? So like it's min of these two, right? So it says, hey, which one is and multiplied by the advantage, and advantage is computed as reward for this output relative to rewards for all other outputs, right? Normalized. Right, and then you subtract KL divergence, like saying, hey, do not go too far from the reference. And their DKL is slightly different. In this particular paper, they don't say why they use this one. Maybe it is explained somewhere. Cool. So what happens with this reinforcement learning is that they begin by having, so they have one network called V3 base. So V3 base is they finished pre-training of the V3. That's, I presume this is V3 base, or maybe that's after supervised fine tuning, but that's before any reinforcement learning, right? They use that to run RL, and so when they do that, RL is working pretty well, but has issues such as sometimes it's unreadable, sometimes it's not formatted very well because for RL formatting doesn't help, right? All it wants is the reward, right? And it can read text which doesn't have formatting just fine, and it mixes languages, right? So what they do next is they train that model. Now they use that model to sample a bunch of trajectories of high quality, right? And my reading of the paper could be incorrect, but I think what they do is that first of all they guide it with prompting, and second of all they use humans to choose the high quality trajectories. And then the next thing they do is they get the base model again, fine tune it on those high quality trajectories, and then do reinforcement learning again, right? And so that one is good. That one presumably doesn't mix languages very much, though somebody told me today that it still mixes languages every now and then, right? And then V3 in particular is also trained on those reasoning trajectories. Question is, where do the rewards come from? So for the original, for the first set of reinforcement learning, right, the one they do to get the reasoning, they use math problems, programming problems, where the reward is exact, right? So there's a math problem that says, like compute something, and there's an integer answer, right? And so the model either produces that exact integer answer or not. It's 1 or 0. Programming problem is the same, right? Presumably, like there's some output it needs to get. Then later, after they do that reinforcement learning, and they fine-tune V3 on that. They do more reinforcement learning, this time not for thinking trajectories, but like for general, like for like how well it answers the questions from people, how well, like how safe it is, etc. For those, they use neural network to give the reward, right? So that, yeah. So then it's not just 0 and 1, I guess. So the question is, how would that work in the areas where there is no explicit reward? So even for the last stage of training V3, they do reinforcement learning for like alignment, right? And there, like I guess a pretty standard approach is you just use another good neural network to tell you how good the output is, right? Because they are pretty smart, and in many cases they can give you a very good value. There's several breakthroughs we talked about today, right? So like the model is cheaper. I think the model being cheaper is just good engineering, right? And there could be multiple hypotheses why that didn't happen before. I guess one of them is that the intersection, the set of people who understand machine learning very well and the set of good system engineers is not as big as any of those two sets, right? So like Meta, for example, probably has very good systems engineers. OpenAI does, but they also not. Well, I guess OpenAI doesn't publish too much of their infrastructure. Specifically for gRPO, that's an interesting question. I guess part of the thing here is that until 01, people didn't know that. It's like a 4-minute mile, right? Like with 01, we all knew now that it's possible, right? And I guess the amount of time that passed is relatively small. So maybe there were other people who were very close to publishing it. Oh yeah, or potentially just the base model finally became good enough, right? Because also DeepSeek V3 on itself is a state-of-the-art model, right? So they're working on top of a very capable model, right? So yeah, like a year ago, you would have, Llama 1. Maybe it just wasn't capable enough. Yeah, I guess we can conclude this part here, and then there's pizza. Yeah, and then more discussion in the smaller groups can continue with pizza. Okay, thank you everyone for coming.